Hello everyone, welcome back to Let's Learn Physics, the show where I explain graduate level physics concepts to curious minds like you. Last time we learned about rigid body rotation, and today we're going to continue our journey through classical mechanics by Goldstein and collaborators with chapter 6, Oscillations. An oscillation is motion like a spring. It goes back and forth periodically. The first section of the chapter is called Formulation of the Problem. Good naming choice there. Oscillations happen when there's a restoring force on a system. That means there's an equilibrium point, and for any deviation from that equilibrium point, there's a force pointing back to restore it. This is in contrast with an unstable equilibrium, where a system might be motionless at the moment, but any tiny little force will cause it to fly away. The example you learn in undergrad physics is of a spring. Extend the spring, it pulls back. Compress the spring, it pushes back. The spring force and spring potential are given by these equations, which you may remember from high school or college physics. The coordinate for a mass on the spring would be x, which equals the equilibrium position plus the deviation. Now remember, we can do physics with generalized coordinates. It doesn't have to just be position. And a generalized oscillating coordinate is also equal to an equilibrium coordinate plus a deviation, which we write as q0 plus the Greek letter eta. And with any coordinate system, we can choose the origin, that is the place where the coordinates equal 0, as the equilibrium point. So the generalized oscillation coordinates are just eta, just the deviation from equilibrium. Now, most potentials are not a simple harmonic oscillator. However, for any potential that has an equilibrium point, if you zoom in closely enough on that equilibrium, it looks a lot like a simple harmonic oscillator. And it behaves like one mathematically, which we can see if we take the Taylor series of the potential around the equilibrium point. Now that's a lot of jargon, but it basically means almost any potential with a stable equilibrium point can be approximated as a simple harmonic oscillator for very small oscillations. The kinetic energy is the same as it usually is, leading to an equation of motion that looks like this. If you're wondering what an equation of motion is, I did a video specifically on that a little while ago, and I used this equation of motion as the example. So that video could be a good supplement for this one. Section 6.2 is called Eigenvalues and Principal Axes. Now it's very math heavy, so I'm going to skip most of it. The important part is that it solves the differential equation by suggesting the deviation is given by this. C is a scale factor and doesn't matter. The AIs are the amplitudes of every coordinate, and e to the I omega t just means it oscillates back and forth. This section uses matrix algebra to prove that there are the same number of vibration frequencies as there are coordinates. So for instance, if our potential is an elongated bowl, then the frequency an object oscillates going this way is going to be smaller than the frequency going this way. These frequencies are called the resonant frequencies. Section 6.3 is called frequencies of vibrations and normal coordinates. Because there are the same number of resonant frequencies as there are coordinates, we can transform into coordinates that each oscillate at only one frequency. In our example of the long bowl, if we have our bowl like this, but the axes go this way and this way, an object won't oscillate on the axis, it'll do something more like this. So we want to transform the coordinates to be longwise and shortwise across the bowl. These special coordinates are called normal coordinates, and they're represented by the Greek letter zeta. Their paths of motion are called the normal modes of vibration, and the actual motion of the system is a superposition of the normal modes. Section 6.4 shows an example of the free vibrations of a linear triatomic molecule. That is a molecule that has 3 atoms and they're arranged in a line. The position coordinates of the atoms are x1, x2, and x3, and the molecule is modeled as if the binding forces between the atoms are springs with an equilibrium length v. Their forces are the spring restoring force, and their potential is the harmonic oscillator potential. Expanded out, the potential looks like this. And that's a little bit obnoxious, and so we will rewrite it in terms of the deviation coordinates, those etas. When we do that, the potential looks like this, a little bit simpler. The section then goes through the math process that we skipped about section 2 and derives the 3 resonant frequencies of the molecule. Now you notice that one of these frequencies is 0. That seems weird, right? Well, that's what we get if the molecule is just moving at a constant velocity without oscillating. That's kind of like drawing a square in 3 dimensions. We can transform the coordinates so that one of the coordinates is redundant. All that's needed to draw the square is a 2-dimensional plane. It's the same with the triatomic molecule. We only need 2 oscillating coordinates. Transforming into the normal modes, they turn out to be combinations of the oscillations of the molecule. For one of them, the central atom remains still, while the other 2 oscillate opposite-wise on either side. For the other one, the end atoms move in tandem, while the one in the middle moves opposite both of them. The full motion of the molecule is a superposition of both normal modes. If we consider 3 dimensions, the molecule can bend as well. So we add in 2 more normal modes, one going like this and one like this. Section 6.5 is forced vibrations and dissipative forces. This section goes into what happens when we drive the oscillations or when we damp them with friction forces. If we add a generalized force, the equation of motion no longer has a 0 on the right side. It has the force. Suppose we add a force that oscillates with time. It's important to note that this frequency of the force does not need to be a resonant frequency of the system. This force causes the system to move with the frequency of the driving force. The solution is this, and we see that now the system does not oscillate at the resonant frequency, but at the frequency of the driving force. Its amplitude is given by this. Of course, the stronger the force, the higher the amplitude of oscillation. But what's that in the denominator? We're subtracting the driving frequency from the resonant frequency. That means the closer to the resonant frequency the system is driven, the higher the amplitude will become. If it's exactly at the resonant frequency, then the math says the amplitude should be infinity. In real-life physics, what happens is that the amplitude gets so large that it's no longer small oscillations, and the simple harmonic oscillating potential is no longer a good approximation. The equation of motion is no longer correct, and the physical system changes so that the amplitude never actually reaches infinity. If we have a dissipative force, or a friction force, that depends on the velocity of the motion, the equation of motion looks like this. We now have the coordinate, its double derivative, and its single derivative in the same equation. The solution is this, or this. The book wrote both of them, and I'm not entirely sure what the difference is between them. The important thing is that the oscillation grows smaller over time, because the friction takes the energy away. The book then talks about damp-driven oscillations, and they show a little less math here. I think they're assuming here that the reader is now comfortable with all the coordinates and transformations, and so they don't have to talk about it again. Anyway, here's the differential equation, here's the solution, and the amplitude is this ginormous fraction. Now, if you notice, for every coordinate, the numerator will cancel something out of the denominator. So driving the system at the resonant frequency no longer blows up the equation. 6.6 is titled the damp-driven pendulum. A pendulum is modeled as a heavy object at the end of a rigid massless rod with its top fixed. I'm sure you've seen plenty of examples. A pendulum has oscillations, but its restoring force due to gravity is not linear like that of a spring. It's based on the sine of the angle of the pendulum with respect to its equilibrium position. So the pendulum equation of motion looks like this. But for small oscillations, we can use the small angle approximation, where the sine of the angle is approximately equal to the angle. In that case, the equation of motion is the simple harmonic motion equation. And the solutions are what we learned in college physics, with the angle being proportional to the cosine of the resonant frequency times time, and the resonant frequency being equal to the square root of the gravitational field divided by the length of the pendulum. The section then goes on to discuss non-small angle motion of a pendulum, including full rotation motion, but that feels like extra off-topic material to me, so I'll leave it at that. That's it for today. We talked about simple harmonic oscillations, about how most potentials with a stable equilibrium can be modeled as simple harmonic oscillators for small deviations from the equilibrium. We looked at the normal modes of vibration and how each has an associated resonant frequency. And we looked at how the amplitude of oscillation changes when the system is driven or damped by a force. Next time, we'll go into Chapter 7, Special Relativity. If you'd like to be notified when that video drops, you can subscribe and hit the notification bell. Let me know what you thought in the comments, and don't forget to like. If you or someone you know could use physics tutoring, you can visit my tutoring website in the description for information on how to sign up for lessons with me. And if you think this kind of learning is valuable, you can support me on Patreon like these cool people. Thanks for watching. I'll see you next time.